Nice.
Can I actually make one?
No. Yes, at home, under the care and supervision of your parents, where I am in no way responsible for you.
Yeah, but they aren't going to let me.
Yes, that's not my problem.
Like, they draw the line of, like, explosive usually.
Okay, notes out from last day. Worksheet out from last day. Go, 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 go.
What are you ready? Oh, over break? Probably not.
And as we're waiting, every single person, please come up here and fill in one of those blocks. Here, let's zoom it in a little bit. No, view, zoom, 150. No, view, zoom, 200. Whoa, whoa, then bigger writing spot there. Nice. I don't know, it disappeared. You can use your finger too, as long as you don't scratch it. Up to 2 people can write at a time. What are you doing? No, it was on pen.
No,
Put
it
it on that
wasn't.
pen.
Yeah, Russell.
No, there you go. Now it's on pen.
It has to be another pen, man. Sorry, which one are you doing? I'll do the last line.
Sorry.
I go up or down?
Belt is so big it feels weird.
That's fine.
Yeah.
It's a nice belt.
It's a traditional kilt belt.
That was mine.
And now that I have gotten one, I'm like, they don't have you wear a traditional kilt belt.
Actually, what do I have to do?
Weird.
Yeah. I feel like it would have been uncomfortable.
Although you're also not wearing the kilt
Can
in
I
the
have
traditional
the
way.
pen?
It should be like up here around your stomach, apparently.
Oh,
Yeah.
that's really too bad.
Yeah. And mine has pockets. One pocket on either side, and hidden pocket for the cell phone in the front.
Listen, you felt like you'd be in charge of making us.
There's a local seamstress that can do that for your kilt. There's lots of people who will take the kilt there and get it done.
Actual
I need that.
Oh yeah, the traditional kilt. You put it on, you basically lay it in the place, then you roll off into it.
There are 2 times a year. I guess my cousin's well. He dresses up full traditional, like traditional bagpipes, the whole 9 yards. Most hilarious thing, so now, he played the bagpipes so that he fell over at one of them there. He's wearing full traditional.
1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you have not yet written up here, there's lots of people who haven't. Please go. Go. Write up your word. Zoe.
I can do it.
Fill in the box. Fill in the box. Ariel. Fill in the box. Oh, you're filling in 2 boxes. Sure. Oh, no. Okay. You filled in. No, stop. Let other people. Yeah.
I have to go get my paper.
We're going to go over
That's my
it.
favorite.
You can't just do it.
Wait, where's the marker?
Right there.
Oh,
It's magnetic.
I knew that. Okay, I'm gonna do this. I want to do it. You do me. You do this one.
What? No.
I need my paper.
You do this with your hand.
It'd be like 20 minutes to figure it out.
You did it
That's
last
it.
Saturday?
Yeah. We did it. You can get that out, so I might be able to take it in here and do it for a little bit. I'm gonna get time for it to work on it after we do the rest of the 6 days, and then the rest of the class we can work on it, and then to think about the water rocket lab. Excellent, thank you. So let me just check. 84.631. So 84.63 correctly rounded. I don't want to do that because it will start writing. 83 significant for you. That should be 84 point. What should that be there?
I don't know.
0.6.
0.6. That is 3 sig figs. To 2 sig figs, that 6 would round the 4, so 85 is good. And to 1 significant figure, 80. You could also write 8.8 times 10 to the 1. 0.95, let's get that decimal in there in case you can't see it. 94500, 4 sig figs, 1, 2, 3, 4, that's good. 3 sig figs. Now, how are these? How are these two numbers different?
Was measured.
1 second, I don't have everybody's attention. I've got Timmy just making a meal. Please put all of that away since it seems to be distracting you. You don't have your notes out. See here, you should have your notes out. You should be ready to go. You don't even have a meal to distract you. And we've got there and there. Zoe, where's yours? Notes. Your notes are on the other side of the worksheet that looks like this. You're writing it on the back, or you can just get out a piece of paper to supplement it. We're going to have 2 more pieces today, and then we're going to be done. But if this is 0.9450, and this is 0.945, they are the same number to a mathematician. Why is it important that one is 4 significant figures and 3 significant figures?
It shows you measured it one further.
It shows we measured it one further. On a practical level, the difference between these 2 numbers in terms of when I go out into the lab, if I bought a scale that measured, our current scales measured to 2 sig figs. They're a couple $100. Getting one that measures to 3 sig figs, probably $1,000. Getting one that measures to 4, a microgram scale, we're probably talking $10,000. School used to have one. Measuring to this level of accuracy takes a lot of skill, time, effort to make a machine that can do that. So although it's the same number, you know a lot more with this one. You know an extra decimal place. But more accuracy and precision in your results. 0.945, we take that 4, round it up to 5. See here? Looking over here, Ben. And so that one's good. And the last one, we have to round it. That is not 1. What would this be to 1 significant figure? 0.9, because that 4 does not round it. You only look at the number right next to it, so this would actually be 0.9, 1 significant figure. Thank you for sharing, but we don't need it out loud. Okay, next one. 4 significant figures, 4.953, good. 7.953 sig figs, good. 7.0. If this 2 significant figures, what's this number to 2 significant figures? Not 0.
No,
8.0. Because that now has to round up, which rounds up the next one. So it would actually be 8.0. So the number of sig figs is right, but we go to that. And to 1 significant figure, that one, 8 is good. Okay, 2,058,268 to 4 significant figures is not 2,058. We need to add 3 zeros. Or you could go 2.058 times 10, 1, 2, 3, 4, 5, 6 times 10 to the 6. Either way, that way you've shown it to 4 significant figures. 3 significant figures, I need to add 4 zeros. We could continue on with that. 2.06 times 10 to the 6. 2 significant figures, so that just continued. Would we round that? Yes, we would. 2.1 times 10 to the 6. It's much easier to use scientific notation for this, and then just 2 times 10 to the 6. Or you could have just kept adding the zeros on just to keep the amount the same. So that is counting and rounding sig figs. But you just did a lab. You have measurements that have given you the sig figs. On the measurement, it said the velocity is this. You write down all the numbers it gives you. You've got your error in the last one. Page width, do that. But once you have it, you are then doing some calculations with it. Multiplying and divided numbers with significant figures. Now, to do this, there is one other thing I have to say, and that is if I have a number like 1.2 grams, how many sig figs is that? 2. 2 sig figs. if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I say 14 scientists, and I counted them, how many sig figs is that?
1.
No.
It does.
It's not 2.
Because you're
It's not 1. Pardon?
It's 3.
Not 3.
14.
Not 14.
5,
5 is closer than the other ones. Not 0.
6.
Not 6. 14. Well, actually, 14 is closer than 5, but it's not 4. 28 is closer than 14.
20?
No, 28 was closer than 20.
30.
30 is closer than 28.
29?
29 is 31 is closer. Yes.
Infinite.
Infinite.
Huh? How does that work?
We assume that if you're counting apples, money by hand, people, number of desks, there is no error in the counting. You might have made a mistake. Please put those away. Like in your bag, get rid of them. Your notes are still not out and you're still not ready to do class. Okay? If you're counting and you miss one, the error is not an error of your counting, it's that you can't see. And so if you're counting numbers are infinite as well as defined numbers. So there is 1,000 milliliters in a liter. There isn't sometimes 1,001 and sometimes 999. It's defined. There is no error because we just made that up. There is no error in counting that it's plus or minus 1. So we don't assume any errors in those. So if I said I have let's do 1.5 times 3.00. Mathematically, that should be fine. What's the answer? 4.5. Now, how many sig figs in this? 2. How many sig figs in this?
1.
That has 3. The zeros in that one count. So then the question is, should our answer be 4.5 or 4.50?
0.
4.50 would make it 3 sig figs. But this one was only 2 sig figs. Where is our largest source of error?
0.5.
One.
In 1%.
Yeah. This one only has 2 sig figs. This is the biggest source of error. It's plus or minus. It's just one known, one guess. Whereas this has 2 knowns, 1 guess. So we assume in our answer that the least number of sig figs applies. So if I have 2.37 times 8.4 times 10 to the 2, pull out your calculators and calculate that away.
Wait, that's 8.1.
8.4.
It's 1,990.8.
1,990.8?
Yeah.
Excellent.
Thank you.
Um,
All in our head. Yeah, all in our head.
now, how many sig figs should it be to?
Or not two.
Yes?
1,903.
It should be to 3 sig figs.
Why?
So, how many sig figs in this number? 3. How many sig figs in this number?
2.
2. So how many sig figs should that be to? 2. So what would this one be to 2 sig figs? Yes?
I just have a question.
Yeah?
So is it just like the last number that's multiplied? That's what like that's what determines how many sig figs can be in the answer.
No, the one with the smallest one. So if for this one, it was the first one. This one is 2, so it's that one, because the other ones had more.
Okay. So it would be 19, wait, hold on, 1.9
2000.
or 2 because it rounds up.
It would be 2. So yeah, it would, because it's going to go right there, so we're going to round it. But if we write 2000, that looks like 1 sig fig. So how can we make that 2 sig fig? 0.0 won't, it's still 2000, that indicates it.
No,
Yes?
20 times 10 to the
So close.
2 times 2.0 times 10 to the
Put a little
3.
K next to
Yeah.
this.
2.0 times 10 to the 3 is still 2000, and we're showing 2 sig figs. This is the purpose of scientific notation, is to show our error. This is like when in physics, students will give me fractions, like, oh, the answer is 29 over 7. What? That doesn't have error. It's not actually 29 over 7. You have a decimal in there. If your calculator does this, this is only useful in math, pure math, because mathematicians don't deal with reality. They just make stuff up. 1.457 times 90. Pull out your calculators. Here you go.
It's 131 times not times 131.13.
0.13. Excellent. Now, we have to put this to the right number of sig figs. How many people think we should put this to 1 sig fig? 2 sig figs? 3 sig figs?
What is that?
4 sig figs? Okay, let's examine it. How many sig figs is this number? 4. How many sig figs is this number? 1. So, what must this equal then? For 1 sig fig? 1. So, what number should I write? How should I write it?
1.
Just 1?
100.
100. We're still rounding. We still have to indicate it's 100. So, we can't get rid of the zeros. But now that's just 1 sig fig. Or, 1 times 10 to the 2 would also show the correct number of sig figs. Get rid of some distractions. Excellent. Excellent. Well done. Perfect. All the way down the line. Okay. 7.6. Divided by 0.12.
63.
Wait. Let's give everybody a chance to do it.
63 point.
I know, but I think I'm going to ask someone over there.
Oh.
I'll go to answer.
Go.
5.
Say it from the beginning. What?
Hold up, sorry. No, I want to answer. 6, 3, 3.3, 3. Infinite free.
Okay. Well, this is now in math. How do they tell you to deal with this in math?
Put it both
You
of
put a line, right? And that's nonsense.
What?
You don't actually know that that's 3 because these numbers aren't that accurate. This could be 7.7. This could be 0.11 because of error. So we don't know that it's that accurate. So we want to go with how many sig figs should this be to?
Infinite.
No. 2. So we should have 63. How many sig figs are in this number? 2. How many in this number? 2. That 0 doesn't count. I could have just written 0.12. It would have been the same thing.
But if zeros are in front, it counts as 1.
Zeros in front count if there's another number in front of it. So if I had 0.0105, How many sig figs are in that number?
No, 4. No, 3.
4?
4. 3.
Nope.
3.
3.
Chatty 3.
3?
Doesn't count, doesn't count, counts.
Okay.
So why doesn't the one in front of the one count?
Let's say that this is 0.0105 kilograms. Or because you're using it out there, that's how many meters? How many centimeters is that? Ariel?
How many centimeters? She's really good at this.
Oh yeah. Okay. Okay. That is 0. Wait. 105 centimeters. Okay. Henry done. Wait no.
Wait, what? Oh, it's 10.5 centimeters.
Henry,
What?
Henry tried to chocolate milk.
Yeah.
That is.
How many is it? What's the number?
Wait. It's 1.05.
1.05. Any other differences?
1.75.
Centimeters.
Thanks.
Pardon?
Isn't it 105?
No, there is.
That's 1 meter.
Oh,
There's 100 centimeters. Is in 1 meter. So you multiply by 100.
You know what?
so like 1 point.
Yeah.
Wait,
Zoe, this is your question.
Wait, sorry.
Timmy.
No. No. I know my.
I think we're gonna rearrange. Timmy, you go back one. Sit here. You come up here. There. Excellent.
So, sorry.
And I might move you two apart.
What?
We're good.
Okay. This was in meters. And then I converted to centimeters. It's the same measurement. Can the number of significant figures change just because you change your unit? No, it's the same level of accuracy. So any zeros that would disappear if you changed it
Yeah.
don't count.
Okay, but the 0 in the middle can.
But yeah, because it's part of the number.
Oh,
And last one, and anybody else who has this question, Zoe, if I put a 0 here,
yeah.
how many sig figs is that?
4.
4. So well, how do I have to change this number?
4.
Wait, how?
That means I measured to this spot.
It's because it's just a 0.
Yeah, and that measures, I measured to here. So I didn't just have, with my centimeters 1.05, it's not plus or minus, 4 to 6 here, it's all the way to there.
But I thought like let's say you change it all the way to 105.0, you can get rid of the 0.
We could have got, let's go back to this example. There, did I have to write those two numbers?
No.
No. So I wrote them even though I didn't have to show how far I measured it. Numbers, zeros you write down
So this
even
is
though you
measured.
don't. So because I did it there, it's because I measured them.
Oh.
Okay?
Yeah, I get it.
Okay? Who needs more examples?
She's smelling fancy.
Zane?
What?
Mm.
I didn't. I made a fart noise.
Ariel? Move over one.
No, but I was.
Zane?
It was his fault.
Back of the glass one.
What did I do?
Zane, what's your favorite number?
My favorite number?
Yep.
Like, I don't know.
What's your favorite number?
My favorite number is
Ariel, I'll move you again.
16.
16. Ben, what's your favorite number? Bertie, what's your favorite number?
21.
Excellent. Do that and give that to me to the correct number of sig figs. No, one over.
How many
There.
sig fig?
Right there.
That guy not sitting next to me.
How many
There.
sig fig?
Oh, never mind.
I'm gonna destroy you.
So we're gonna hug him. We're gonna hug him. He's a good influencer.
One over there.
Let's take
Go to
you want it done?
Yeah.
Hmm.
Don't specify how many sig fig.
So here.
Over there.
Don't if I see you. Don't if I see you.
Maybe not for long.
Yeah, honestly.
Okay, answer to this one. Zane.
0.765714.
0 point.
765.
No.
7. 114.
I think, oh,
No. 140.
oh, 1 4. Okay.
Yeah. 285.
No, we can stop there because we know how far we should go.
Go back to the
Huh? Ariel?
Distracted.
Yeah. Ariel over there. Hugo over there.
No! Okay then. Well, I have the answer right here. It's musical chairs.
That's okay. How many sig figs should the answer be to?
Hello, Ariel.
2. So this answer is actually
I'm so great. I'm so glad.
7
I
6.
love sitting here.
7.
Ben,
We're so fast.
what would that number be? Given the 5 next to it?
7.
Yeah. So it's 0.77.
Hello, guys.
Shouldn't it be 0.8?
Oh, time to log in.
Why?
It's not 0 sig figure.
How many sig figs should this answer be to, given those numbers?
This is so weird.
Right?
Hugo,
Sorry.
2. And this 0 doesn't count for sig figs. So we need 2 sig figs. Okay? Last one. Actually, not last one. Go back. Do these two.
I don't have the sheet.
Go come up and get the sheet.
My sheets is in my. I already finished it.
Well then, you write it down on a separate piece of paper, do it right now, it's on the board. And see here, even if the sheet was in your room, I'd expect you to get a piece of paper and follow along.
Pretty sure you did them.
Pardon?
I already did them.
That's good. I can see everybody in 2 seconds. I don't know how you did though, I hadn't taught it yet.
Yeah, we did. We did it as a class. Yeah, we did.
But
as a class.
did we do the multiplication?
Yeah. Well, I
Wait.
did.
Don't you just put it in a calculator?
The answer is 747.84.
I mean, they're all 7.
So, Bertie, what's this one?
747.84.
747.84.
747.8.4.
Oh,
That's what you take it
8.4. But what is it in centimeters? Now, what is it to the correct number of sig figs?
That's shit.
That is not the correct number of sig figs.
Oh.
Yes?
So it's 747.8.
7.
Oh.
That's a different number.
750.
It's 747.
Whoa. Before we do anything else, do I have the right number up here?
No.
Oh.
So my mistake was I believe someone when I shouldn't. 747.84.
0.84.
Good one.
You were right.
Ariel,
Yes.
what is that to the correct number of sig figs?
Is it 750?
750. Nice. Our smallest number of sig figs up here is how much? 2. That's 2 sig figs there. That's all we need to do. Second one, what's the number for there? Alejandra? What's the answer for this one?
106.07.
400.
No, 106.
406?
106.07.
Bertie.
What?
And what is it the correct number of sig figs?
I don't know. I know it's 11.41.
Oh, everybody get a completely different number? Yeah, I thought 34 divided by 3 should probably give you around 11.
It's 11.4.
No, Alejandra, go.
41.73.
And what do we do with the units, meters over seconds? Meters per second. So now our units are coming into it. And how many sig figs should this number be to? Timmy? How many sig figs are in this number?
I can't see it.
34.8.
Oh, 3.
3. Perfect. And how many sig figs are in that number? 3.048.
4.
4. 4. Can you not see from there?
Not particularly.
Hmm. Maybe I will move you as well.
I'm sorry. Hi, Johnny.
Timmy, go there. There's musical classroom today.
I move.
No, you're good.
Can I move back?
No.
Oh.
Yeah, can you go come over here?
This is one.
Don't make me move you to the lab. What? So, no, Timmy? So what? Where are we? There we are. So what is that to 3 sig figs?
11.417.
3 sig figs.
Oh,
So
11.4.
11.4. And then you keep the units. Last one, and then I will stop teaching you sig figs, is adding, subtracting. Pardon? For adding and subtracting sig figs, we do it a little different because we can get down to right where the error is. If I have 5.0, what does that mean in terms of error? Where's our error? Plus or minus what?
It's just 1.
1?
Yeah. Or 2.
2?
1.5.
1.5? Where do we assume the error is?
I found on. Oh no, it's
0.1.
Oh, what?
That's where we measured to. So that's our error. And it's always assumed to be plus or minus 1. If I have 587, what's the assumed error for that number?
Is it 1?
Why is there a line under?
Plus or minus.
What's it? Naomi, what was your question?
Why would we just put like plus or
I did put plus or minus.
minus? So like one and the other.
Did you take the picture?
Because it's plus or minus. So if I say 5.0, that means it's either 4.9 or 5.1. That's what error means when you take it. That number's not certain, it varies. And if a different person took the measurement, or if the machine, you know how you see the last decimal flicker when you're taking measurements? That's the inherent error. Yep.
Wait, but like y point 1.
How many sig figs does this have?
1,
No. 5.0?
2, 2, 2.
It has 2 sig figs. This is certain, we know it's 5. Here's our error. What decimal place is that?
Wait, what? Repeat?
What decimal place is this?
Like 10?
Yeah, it's just 10. So our error is plus or minus a tenth. That's the last thing we did. So it's just 0.1. For 587, it would be plus or minus 1. Because it's there. If I had 560, this would be plus or minus 10.
What?
Because this 0 doesn't count. There's no decimal there, so that gives us plus or minus 10. If I had 500, this will be plus or minus
100.
100. Alejandro, question?
What is that number?
This one? 587.
Yeah, why isn't that plus or minus 100? Because it's still.
Because we can tell we measured to the 7,
Oh, it's on the zeros.
right? Only zeros is, and if I wrote 500 decimal,
Yeah.
that would be plus or minus 1. Because I said I measured all the way to the 1 spot.
Whoa, okay.
Does that make sense? Yes.
Who invented this thing?
Scientists, because we got to explain the error. If you're building a bridge and it has to hold, say, 100 tons, and you build it to 100 tons, but all your measurements mean that your error is plus or minus 10 tons, then something that's 90 tons could go across it and break the bridge. So we need to know what we know. There's a variety of different types of knowns and your unknowns. There's your known knowns, your known unknowns, and your unknown unknowns.
How do you know an unknown?
The knowns, unknowns are your measurements. Your unknown unknowns are the things that'll break your bridge that you never thought of. We can't do that. We just, yeah. A Sharknado would be an unknown unknown.
Nuclear bomb.
But measurement, we know our error. We might as well calculate it, make sure the bridge will hold. Make sure the aircraft will fly. See here? You're just playing with your calculator. Focus. Excellent. And take away the cell phone, and the calculator becomes just as interesting. Okay. So does it make sense if I had, let's say, 55 plus 0.567. What is our error here? What is our error with 55? 1. And what is our error with this one?
100.
.001. Which is the most important error? 1. So we would say, oh, that's the one we're going to worry about. So when we go 55 plus 0.567, we're not counting sig figs. We would just go, that's the one, but this is the biggest error. Plus or minus 1 is so much bigger than that. We will just go 55.567 round, because that's our sig figs, and it's 56. We keep the same place. We're no longer counting sig figs. We're looking where it goes to. So if I have another one, 592.3 plus 0.2. Give me that to the correct number of sig figs. Sorry?
593.
Nope. Yes?
6?
Just 6?
No.
Well, cause here's my explanation.
Yeah,
Oh,
go.
no. It would be 6.1. Because 592.5, because the
Okay, I'm going to start off with that, because that is a number we're going to use.
because the smallest number of significant, well, whatever, is 2.
Zane, please go back to paying attention, get away from the wall.
So it would be, you move it
That
to
side.
2, which would be 5.9, which equals to 6, and then it would be 6.
You are counting from the smallest number of sig figs, right?
Yeah,
So you're going, how many sig figs is this?
2.
No, it's 1.
What? But
Well,
you said
the 0 in front doesn't count. We've already done that. Yeah, no, it doesn't count. You're not allowed to make it count.
Okay, so
Okay.
so it's just 6. I was right. Cause you move it.
How many sig figs is that?
4.
4. But this is addition.
Oh! It's just 59. It's just 59.
Nope.
Because you put it up 1.
No, it's 60.
What?
I have no idea. Can we know the answer?
Hey, stop. Okay. I have to deal with 2 things.
That is what
Stop.
I said.
Stop.
Is it just
Nope,
59?
stop. There's one fundamental thing. Whatever this number is, it's close to 600, right?
Yes.
So you can never say 60. You can't make the number bigger or smaller.
You move the dot.
No, you're not allowed to move the dot.
You move the dot every other time.
I've never moved the dot.
Is it 100?
60 times 10. The dot.
Let's go back.
93.
No, Timmy, focus. In all of these examples, let's go back to our sheet. When we were rounding, 84.63, 84.6, 85, 8, 80. The dot stayed in the same spot every time. 0.9, 0.9, 0.9. The number, we cut off numbers, but the dot never moved. 7.95310, 7.953, 7.95, 8.08. Dot never moved. 2,058,268. We corrected this one to show that the dot never moves. and we converted to scientific notation. It's always times 10 to the 6. The dot doesn't change. You move the dot if you make it scientific notation, perhaps. That may be where you're thinking about it. Yes.
Is this gonna be on our final?
This is on your lab.
Bam. It's on our final.
But is it like in our final?
Yeah.
Oh, shit.
Yes?
Yeah.
It's fine. In the finals, that's cook.
You know, yeah. I let this cook. Let this cook. Just let it settle. Let it go in. The reason being, the same confusion happens next year in Chemistry 11 and Physics 11. I'd rather you hit this now, and then next year it goes, while everybody else is confused, you go, oh, this is actually not that hard. Okay?
Back and I forget.
Yeah, me too.
You may be regressing, but let me pull it down. Written this way, it might be more confusing. If I go 592.3 plus 0.2, what is the error on this one? 0.1. What is the error on this one? 0.1. So what error should our final answer have?
0.2.
To be honest, you are actually more correct now than I'm going to teach. Because in university, this is a very simplified form. We would add our errors up, but we'd use calculus. So it'd be actually slightly less than 0.2, but slightly more than 0.1.
But that makes sense.
Okay, I got it.
No. We're not going to ignore that.
No, I got it. 0.15.
I don't get
Is it-
it.
is
No,
it-
stop doing that. Stop doing that.
That makes sense though.
The error is in this place. The reason, everybody else ignore me, I'll explain just to you two. The reason they don't just add up, if it's plus or minus 0.1, half the time it could be minus and the other half it could be plus, right? Which means some of them cancel out. And you can't just pick the half either. There's a more complex calculation that you'll get to in third year statistical analysis. We're not going to do that. The simple version is, for just two of them, it's roughly 0.1. The error is in the 0.1 place, so your answer would just be 592.5 because it's still plus or minus 0.1. For adding and subtracting, you look at the placement, not the number of sig figs. So although this has one sig fig, they're both to the same placement.
So it's not 5.
So I was right.
So this is the right answer.
I had a question.
You did see.
I had a question.
Yes.
What if it's like 500 plus 10 or 500 like
I would like to do examples. So give me 500,
like point whatever, point 1
0.1
plus like 200.1
plus 200.1
plus like 5.1
plus 5.1
plus 0.1. Like this is
plus 0.1,
is this still
505.4.
705.
Oh, what?
That's wrong. 700.
But 700, okay?
oh.
0.1,
So then what's the error?
the error is plus or minus 0.1.
Okay.
So you
So
can
that's
add
all
an
you have to
infinite
put.
number
That's all
of
you have to do.
point ones and it's always gonna be point 1.
So for adding and subtracting, it's 10th, 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 so errors in 10th.
What about
But you
multiplication?
still like.
So multiplication, like let's say I did 1.1 plus 1.1 plus 1.1 plus 1.1, and I did that 700 times. What is an easier mathematical way of doing that?
Times 770.
700, say decimal if we want to make it, times 1.1, right?
Yeah.
When you add, this method of sig figs works for small amounts of adding. But when you start multiplying, that's when we go, oh, what's 700 times 1.1?
770.
770. We would go, oh, 2 sig figs. 770 looks good. That's 2 sig figs, that's 2 sig figs. We use the multiplication rule. Because those errors do add up over time. And over 700, it's going to add up. But when we're just adding a couple numbers, we just go by place. Because they don't add up that much.
So
Now you are immediately getting into the deep philosophy of what sig figs is. Do they not add up in the same way? I need to teach you a little bit of calculus and integration to like fully explain it. So you have to know a bit more math, but you're like right there. You just don't have to worry about it quite yet, but if you really want to, I can dig out my old text. Yeah.
So when we're adding and subtracting, we just accept our fate and admit that there's like an error there, and we just
When you add up,
we just like leave the error there, like
Yeah.
inaccurate.
well, it must be inaccurate. You measured it. The only things that are true are the things humans made up. Anything you measure in the universe has to have error because you measured it. There's no such thing as a perfect measurement.
Yeah, there is.
Name one.
For the pound there, we measured the exact amount of silicone atoms needed to form 1 kilogram.
If you count the number of atoms, which we cannot do, even then there could be a mistake in counting. But that has an accuracy. The reason
you're
we
saying that if you count it, your accuracy is infinite. It's defined.
no. Let me if you wanted to weigh not silicone, let's say number of lead atoms, they actually, it's accepted that we just assume that they're all the same mass. They're not. There's very, very slight variation. But if you count them, you will get a mass. But there's a limit to how you measure that. Your instrument has an error in it. Now, if you say, and this is now getting to the philosophical side, all the way to when I said infinite for defined numbers. If you say this many silicon atoms is this amount of is this mass,
Yes.
you have defined that. That is an infinite number of sig figs. You just made it up. So it's true because you just invented it. It's not true because you measured it. There's nothing you can measure that doesn't have error. Any observation has error. The fundamental part of science is that our universe is inherently limited by what we can measure. And so it has always doubt. If you're a mathematician, none of your stuff has doubt because you just make crap up every day. Like, Ms. Walensky knows someone that does like 9 plus 6 is 3.
But what about if you measure like nothing?
she's right.
If you weigh nothing?
Pardon?
What about if you weigh nothing?
What if you
Then
weigh?
Technically, then it's just 0 on the.
No, if you get on a scale, like if you weigh, like get on a scale, that last one will flicker, right?
Yeah.
That's the
Yeah,
error.
what if you weigh nothing? Like literally weigh like nothing. And they said
How many of you took a measurement of the carts and when it wasn't moving, it still had a very small velocity?
Yeah.
Your instruments have error. Yeah.
But like, what if there's like a scale and you put nothing on it and it says 0?
I will often take out. What's the first thing you do when you have to take out a scale? What button do you press? Tear to tell it that that's 0 because it doesn't know. And there can be air pressure going by that may cause it to move. Sarah, what are you doing?
What about in a vacuum sealed?
Yeah.
Or a vacuum sealed, sorry. And you have a scale
Yeah.
and you're measuring the weight of nothing.
Yes.
Is that technically perfect?
No, because it is only weigh like that machine can only weigh to a certain amount of mass. So what you're saying is if there's nothing there, there's nothing to weigh. So that should be 0 infinite. You don't know there's nothing there. There could be a piece of dust that just hit it, and you don't see that reading.
Well, if you like vacuum it.
So that you made it impossible for the dust to be there.
Yeah.
But if there was a piece of dust there, it still wouldn't make the reading. The error is inherent in your machine. You can't make it more accurate. Now you could claim, like, again, this is advanced sig figs, and I've done this on a lab report, where I say my actual error was this, because we took these precautions to improve the error rate. And so you do a little calculation, you show why it's better than some of these simple ones. So yeah, you can do things to improve it. But like if you go in there and you look at any of the flasks, the very accurate flasks, it'll say like 250 mils plus or minus 0.0025. They tell you the error right on the flask. Because you've paid for that low amount of error. The ones that are just a graduated cylinder, they're plus or minus like 5 mils. They're like incredibly inaccurate. Because they're just printed stuff on the side. 5 mils. Now, does anybody have an example they want me to do? Just try and work out anything they might think. Yeah.
I just have a question.
Yeah?
So, wait, can you go back to the, like, so is it technically just like you're adding all of them?
Yeah.
But you're just like adding them, but the whole thing is just adding the plus or minus?
Yeah.
Is this just like the amount of like decimals or like?
That's just the amount of decimals. So if I had like 50.03
Yeah.
minus 2.007,
Yeah.
right? Then where's the biggest error?
Point 0.02.
No, just in the placement, like one decimal place.
Like 0.01. Or 0.000.
Do you have the answer for this or something?
No.
Okay, no, just like in terms of this place, that place, this
Yeah.
place, that place, this place, that place, this place, that. In terms of like this area, this area, this area, this area, this area. Where is our error?
The 7. Wait, I don't.
Where is our biggest error?
Because I thought you said it's 0.0. So, because like 50.03 is 0.01.
Yeah,
And then 2.007 is 0.001.
yeah. Which of those numbers is bigger?
0.01.
Right. So that's our biggest error.
Yeah.
So we will take our decimal place
Oh,
up
0.03,
to
sorry.
this point, right there,
Yeah.
and we'll cut off. Other than using it for rounding, we'll cut it off.
And then we'll, at the end of it, we'll just put plus or minus.
Yeah, and
0.02.
and the plus or minus is
0.1.
just assumed. You don't even have to write it down. I was just doing that to show you what it was.
Oh.
So 50.03 minus 2.007. What is that as a number? Yes.
I have a question.
No. What is that as a number? That's what I just asked.
52.03.
What is it?
Are we minusing?
No,
or
it's
plus?
minusing.
Oh,
Oh,
40,
minus,
48.
48
0.03.
0. No.
Oh, sorry,
Point
0.02.
2, 3.
0.05.
What?
Points
No. Give me all the numbers. Just tell me all the numbers to begin with.
48.203.
48.23.
48.023.
Is that good?
Yeah.
Okay. And then we go. That doesn't round it,
Yeah.
and that one doesn't count. So our actual answer is 48.02.
And we don't need the plus or minus.
And you don't need the plus or minus, which is right.
Okay.
Oh, okay.
Okay.
That's, okay.
Yeah. The plus or minus is assumed, and I only include it for like what it means. But if you read this number, a scientist says, "Oh, that's 48.02 plus or minus 0.01," unless you're told differently.
Okay.
Okay,
Okay.
Alejandro,
Yeah.
you look frightened for a moment.
What?
No? Yes?
How'd you get the 2, 3?
Oh, 50.03 minus 2.007. Punch it in the calculator. What do you get?
Oh, because it's like 30 minus 7. Which is
Yeah.
Oh, that makes sense.
So if I had, what numbers could you give me that you want to test? Like, let's take, again, 50.03. Let's minus, what number down here would you find confusing? What do you want to see done?
5.
Minus 5.
Wait, what?
Perfect. So 50.03 minus 5, what do you get?
45.
Yep,
45.03.
45.03. Now, what is this to the correct number of sig figs? Yes?
Because there's four. No, actually, the first one was 4 significant figures, and the second one is 1. So it would be 4.5, right?
Don't move the decimal.
Oh, wait. It's 4, 5,
45.
45.
5. Yeah.
Yep. This was 4 sig figs. This was 1 sig figs. But none of that matters. Because we're adding and subtracting. This is the ones place and the hundreds place. Ones place is a bigger error. We go with that error. Yep.
Can't you just technically say that there is no right or wrong answers?
No, because there is a right answer. If you said 50, you're wrong. It's 45. It could be, because it could be 46, and it could be 44. But science isn't about saying it's like we don't know anything. It's about saying this is the limit to our knowledge. We know what's in here. We just don't know exactly where. But if someone came up to you and said it's 132, like they're wrong. This is when I encounter people who are like in the last thing, like with COVID, is like, nobody should wear masks because of, and then show a thing with error. And it's like, that's not what that says. It shows it definitely helped. You're using the error to say we don't know anything. We know this. We know the range in which we know.
But like 50.03 minus 5 was always going to be 45.03. Like
Yep.
it won't be 46 or 44.
Right. Well, but remember, this is plus or minus 0.01, right? Sorry.
Unless these
This
numbers
is
are
plus
rounded.
this is plus or minus
Oh,
0.01, and this is plus or minus 1. So you could actually be minusing 6 or you could actually be minusing 4.
To account for the error.
Yeah. So you're
Okay.
this is your biggest error
So why did they put 5?
because that's what you're. If you're measuring velocity
Yeah.
on your cart and it gave you 5 meters per second, that means it's only measuring in meters per second. Your cart, it might actually be 4 meters per second. It's just really bad at measuring. It could be 6 meters per second, but it's not 7. Now your cart doesn't measure that grossly. It was like, what was it, like 0.763 or something like that?
Yeah.
So it's measuring that one, but it's not actually. Would you bet your life that was a 3?
No.
No. You'd probably be more comfortable betting your life it was that 6 or 7. Probably really the 7, maybe the 6, but that could be 4. That could be 2, right?
Yeah.
So if I measure something, like if I'm measuring with a meter stick, and I measure with this, and my life depends on the number, and I say, oh, that's 4 millimeters. Are you going to trust that tiny little measurement? No, it really is 4 plus or minus 1. It could be 6 millimeters. In fact, with my glasses, maybe it's 7. And it, you know, it could go either way because that's where our measuring is limited. Okay. So if you have that, that's why we limit it because this makes it plus or minus 1. That makes that plus or minus 1.
Okay.
We just don't write it in. And this is where I get to tell you the joke. 2 plus 2 equals 5. No, 4 very large values of 2. Because this is plus or minus 1. That 2 could be 3, right?
Yeah.
Yeah. So this could be 3. This could actually be 2, or it could be another 3. In fact, that could be 6. If this could equal 1, that could equal 1, then this could equal 2. So 5 plus or, you know, the idea that it's 4 plus or minus 1, it could be 5. If I had 2 kilograms on a scale, and the scale only went to the nearest kilogram, it could be 3 kilograms. It's not just doing a very good job of measuring.
Shouldn't it be 4 plus or minus 2?
Because they vary in a way that can cancel each other's out, because they should be truly random,
Yeah.
it doesn't fully add up in that kind of way.
Okay.
That's the part that requires
But, like-
calculus. Yes?
Is that what you told us in one class that astrophysicists run down like number pi?
Yeah.
10?
Because for them, dividing everything or multiplying everything by 3.14, their error rates is in hundreds of millions of kilometers or stars. And if you just have like 300,000 and you divide by 10 and you get 30,000, that's actually within their error range. Using pi as 3 doesn't matter. Yeah. Like, what is the square root of 2?
Like 1.41 or something.
1.1.
It's like
1.41421.
Yeah. So, to a chemist or a physicist, there is no such thing as a square root of 2. It's a mathematical operation. It's 1.41 to 3 sig figs, because that's how much you had in your measurement. You don't care, it's a square root of 2, it's just 1.41. If you're an astronomer, it's probably just 1. Makes no difference. But if you're a mathematician, have you seen the meme, math is math? Mathematicians going, root 2 is root 2, because they want all the decimals. We are done sig figs. You have the rest of class. I was hoping there's going to be a bit more time, but you have a few minutes left. All your calculations in your lab, because the calculations are fairly simple, part of what we're going to be looking for and marking is, are they to the correct number of sig figs? So there's an adding section where you have to add your masses, and there's a multiplying section where you use the formula.
We have to do our labs now.
Okay? So if you're using a formula, how many sig figs does a half have? An infinite amount, because it's just in the formula. You don't have to worry about it. But the numbers you put in here will have sig figs. And you just use the one with the smallest amount to make your answer to that one. Yes.
I have a new one because I wrote it in pen.
Oh, there should be more labs up here. What? Hold on. What do you need a new one of? The lab.
Sorry about that.
Come up and look. Oh, here they are. They're also printable off the website. I think this is the last one.
Try to write something.
Okay.
You don't even write.
You were to the what? To the correct
You got
number.
your labs? No, we weren't here Saturday.
You took measurements, right? Those have sig figs. Everything calculated from those measurements will have sig figs.
What did you
Life
do?
is error.
Pardon?
Life is error.
Life is error.
So it's a lie.
Yeah. Math is a lie.
Are we
When,
really here? I think.
okay, don't do that.
You won't just gonna keep spinning.
If, like,
Mission info.
one of the problems we had with things like climate change is scientists would say, if you pump this much CO2 in the atmosphere, here's how much the plant will work. And then a news person or a business person will say, do you know that to 100% accuracy?
Yeah.
And every scientist would say, no, of course not. There's just error and then describe all the error. And then people would go, oh, I guess it's not true.
Yeah.
And that's not the way science works.
Well, what's the point of like acknowledging the error if you could just ignore it?
I'd like bringing it to a practical example. You have a plane, and it has to support a certain amount of weight.
Yeah.
If you're measuring how much weight that wing can support, and your error is plus or minus like several tons, then you might build the plane too weak. You have to make instruments that will measure it to the right amount of accuracy, so you know that when a big wind hits it and the stress gets high enough, you know the wing won't break. Because if you have an error, let's say your number is like 2 to 4,
Yeah.
you have to build it so that it can withstand 5, right?
Yeah.
Because whatever's going to hit it is going to be somewhere in here,
Yeah.
so you know build it to this amount.
Okay.
You can build it to exceed the error.
Okay, so it's almost like if you make an error, you'd rather have it like at a bigger error than
Right.
like.
You'd like to account for that
Yeah,
error so things
okay.
don't fall down.
Okay, that makes sense.
Yeah. Yes.
How do we know?
I was actually
You
scared
use your
of
measurements. Then those tell you how many sig figs there are. Your measurements are your measurements. They have a certain number of sig figs.
How many should I put them to? Like,
You're actually.
All the ones they gave you.
What?
And this is
So
your
I think you're just using it.
how accurately to measure it.
When you were like,
that's what I'm like.
Yeah.
seconds later.
So is it okay like that?
Yep. Yes, Ben.
What's the point of it? Just unpack it.
Zero.
That was so funny.
Unless you measured that. Like, did you measure 9
Chat, time for lunch.
Then, is that zero part of your sig figs?
It's lunchtime.
Okay, so it's about.
3 minutes until lunchtime.
Oh, because it's not 91, it's just 92.
All
That's how we got. We skipped through.
I know this was very exciting. To be honest, I've never had a more exciting sig fig class. This has made my day. You were all so curious. This is fantastic. I apologize to those who kept 11. It was probably very boring. However, next project is the Rocket Lab. I didn't get time to post it.
That's so tough.
I will post it. The key part, why I'm telling you early, is you have to have a bottle that had some sort of, pop or something in it. It has to be pop. It has to be carbonated drink. If you bring a juice bottle, it won't be able to withstand the pressure you're going to subject it to get it up in the air. Juice bottles will just explode on the stand and won't go anywhere. But if you have like a Coke bottle, any kind of soda, if you're American, or pop if you're Canadian, will work. Yeah. But also, no glass. No glass bottles. Yes.
I've heard those things that I don't know how to say it in English, but those things that turn off fires, that you just,
Yeah.
those things, if you agitate them and throw them really high, and then it goes like.
They're under an incredible amount of pressure, and so any amount can escape. They can. That's the kind of rocket you're making. You're going to put mass in it. You're going to put it under pressure, and then the mass is going to leave, and then it's going to go. Okay? I am going to post. One of the things that's difficult about the rocket is if you don't put the fins and weights in the right spot, instead of flying straight, it's just gonna do this. So I'm gonna post some background that you should read and watch before you do this. Fins are kind of weird because the weight's all at the bottom. Whoa,
What?
Wait for a minute.
but Bella has not gone.
Yeah,
It's still.
Oh,
I've got 6 seconds.
15.
It might be 4 seconds. It might be only 1 second. Okay.
Yeah, but you're
I got
Is there
error.
error in time?
I-
yeah.
You're forgetting the error.
Is there error we can't
What?
Is there error in time?
There is error in the time.
Yeah.
In fact, if you
Okay,
update
whatever.
your computer, it will tell you the error in the measurement between here and there.
I will. Yeah.
Listen,
Wait,
because you're using what, water and liquids on these sides?
Yeah.
The water's down here, the air's up here, this side's gonna wear way more.
Yeah, you don't want it the weight at the bottom. You want the weight at the top.
Why not the weight at the bottom?
Okay.
If weight's at the bottom,
No.
Air- lighter
No,
things
it's
at the top.
it's about your center of gravity. So if your center
Yeah.
of gravity is at the bottom,
yeah.
right? And air. So here's your center of gravity, right? Push the top. Right.
Yeah.
So as soon as it hits the air, so let's say it starts flying sideways,
Yeah.
the air friction will continue to push it sideways and go the wrong way.
Yeah, but it can also push on the
But
back.
if you have a center of gravity here,
Yeah.
and air pushes on it, this is now the smaller area, this is the bigger area, and it pushes it this way.
Thank you, Mr. Annabelle.
And so the further forward your center of gravity, the
Yeah.
more it self-corrects. The wings help that self-correction.
By adding
So
more
if-
mass.
by adding more mass there to make sure that that does that.
Yeah.
And you want actually, because you're going to put a bunch of water here, put it in push and go.
Yeah.
It helps if the mass is up here, so that this is the one that's swinging to correct.
Right. Sort of like an arrow.
Yeah, exactly like an
Yeah.
arrow. Yeah, it's exactly like an arrow.
Yeah.
You're making
But the
a
thing
rocket
is
arrow.
with like arrows there, so long as arrows will self-correct, even if like they aren't spinning, or even like just because what'll happen here is as it goes, the back will go and go.
Yeah,
because
because
arrow hit
it's using the
both
body to correct.
Yeah.
But if you put feathers on it, the reason they
It works
invented that,
better.
it works better.
But then you can also have shorter arrows. That was the whole reason behind the feathers, was shorter
Yeah.
arrows. and
You're
you still
building
fly.
a stubby rocket.
Because like you can have a long arrow and then you don't need any fins.
But you're
on the
building
arrow.
a pop bottle as at most that and that wide.
Can
You
we just
need-
make bow and arrows
The,
instead?
I have the example, the one that won last year. The one that won last year.
Yeah.
And sometimes they put clay in it for weight because we don't have that many pennies. This one, I think,
Having
no,
it
that's not the one who won. Oh, hold it.
Having it spin.
It is actually because I don't have another one. So this one like that.
Okay, that'll have it spin.
Yeah, and they put weight, and I think actually the tape added way more weight, and they put no tape down here.
So
And
would you recommend just having the fins on the back, having it sort of spins, and then go for as little weight
if
as
you can be
possible?
consistent about it, I suggest for people who haven't built one before, make them straight.
Yeah.
But if you can get some rotation, that will add to the effect.
Yeah.
But if you just
Are we doing this after break is when it's happening?
Yeah.
Or before?
after break most likely.
So can I 3D print fins and help?
Yeah, if we end up doing it after break, that'd be fine.
Okay.
You just need to get your and you weigh it and all sorts of stuff.
Okay. Because if I can have it spin, then I want it as light as
Yeah,
possible.
do I have another one? This one did decently well. And the fins are actually too high. But again, a bit of a spin. Like I wouldn't have predicted this one did as well as it did. But I think it was a function of the fact that it is fairly thin for how long it is, and the fins were big enough that it worked reasonably well. This one I think was just pretty. Well, this one, let's see.
Can't imagine.
This one had
Because
a
the
nice
fins
top to
were,
it.
like sort of
And
straight in the middle.
huge fins.
That's not going to work. Because if it's in the middle, right now what's going to happen is it's going to hit both sides of the fin.
Yeah.
Because you want it only hitting the back side.
One of the things too is you want it to fly straight because you're trying to take a picture and you're going to mark the flight to calculate the energy. And if it goes flying off to the side, you're not going to get it.
Yeah. How high do you usually go?
A decent distance.
70 feet?
I can't
100?
remember, but a decent distance.
Yeah.
Yeah.
And how much pressure do they put in them? Because I know we used to do it at like the Bible camp a lot, and or the
I
camp
have
that
to
go
double check it. It was like, was it 30 pounds, 60
Okay.
pounds? It was some. There's
Yeah.
there's a amount in the lab that we pump up to. There's a certain amount. It says because we usually literally use a bike tire pump, and we pump it
Yeah,
into
okay,
there's a
well,
mechanism that
We
goes
used
on
an
there.
air compressor. We just sort of went
Yeah,
until the
that
part
would
that
do a
would
lot
hold the
more.
plastic gave out.
We don't use an air compressor.
And what ends up happening is it really just comes down to we've had it before.